Welcome to AI Paper Podcasts. We skip the chatter and get right into the research that matters. Today, we're tackling a really critical piece for anyone working on LLM agents. It's a paper called MCPMark, a benchmark for stress testing realistic and comprehensive MCP use.
Yeah, this one's important. It's a bit of a wake-up call, actually. It introduces something called the Model Context Protocol, or MCP. Think of the MCP as the standard way these large language models get their eyes and hands to interact with the real world. APIs, databases, web browsers, all that stuff.
Right, so it's foundational if you want LLMs to act as, agents.
Exactly. It's the bedrock for general agency.
Okay, so the researchers felt existing tests weren't tough enough.
Pretty much. They argued current benchmarks were too simple, mostly reading data, not deep interaction. They didn't capture how messy real workflows get.
So MCPMark is the answer, the stress test.
That's the idea. They built 127 really complex tasks. These run across 5 actual production environments. We're talking Notion, GitHub, local file systems, PostgreSQL databases, and even browser automation with Playwright.
And it's not just reading, it's the full spectrum: create, read, update, delete, CRUD operations.
Yes, and demanding ones. These tasks aren't quick hits. They force the models into long interactions, averaging about 16.2 execution turns per task. That's where things start to break down.
Okay, headline result. How did the big models do?
Well, they struggled severely. The best one they tested, GPT-5 Medium, only passed 52.56% of the time on its first try. That's the pass at 1 score.
Only about half.
Wow. But you mentioned reliability being key.
Right, the crucial metric here is pass 4. This isn't just can it succeed eventually. It's can it succeed reliably, every time. All 4 independent runs have to pass.
And how did GPT-5 Medium do on that metric?
That's where it really hurts. The score plummets to just 33.86%.
Oof. Less than 34% reliability for the best model. Exactly. It basically proves that these multi-step agent workflows, as they stand now, are just too unstable for serious real-world use. There's a major reliability gap.
Okay, definitely a lot to unpack there. Let's get into how this benchmark is designed and why it's exposing these deep problems with agent stability and generalization. So for our audience, who are likely deep in this stuff, the idea of an agentic era totally hinges on the LLM being able to do things, right? That's where this MCP standard comes in.
Precisely. It standardizes the interaction layer.
But what was so wrong with the older benchmarks like MCP Evil or Live MCP Bench? Why weren't they enough?
Well, the main issue was they were just too shallow. They were okay starting points, maybe, but they often used synthetic tasks or didn't require much back and forth. If you look at the numbers, Live MCP bench tasks averaged only about 3.2 turns. MCP Universe got up to maybe 6.8 turns on average.
Still way less than the 16 turns in MCPMark.
Right. And those older ones were heavily skewed towards read operations, fetching info, not really changing things complexly. Real work involves creating, updating, deleting complex sequences.
So MCPMark was built out of necessity to mirror actual user scenarios with these more involved multi-step workflows.
Exactly. And they didn't just dream up tasks. They used a human AI collaboration pipeline to generate 127 high-quality tasks. These tasks are built on 38 carefully curated initial states like pre-populated databases or existing code repositories. And crucially, everything is programmatically verified, so you know if the agent actually succeeded or not.
That programmatic verification is key, avoids fuzzy human judgment.
Absolutely. And those initial states are super important for realism. You're not starting with a blank slate.
Like using real Notion templates or GitHub repos with history.
Precisely. The agent has to understand and work with existing stuff, which is much harder. It immediately introduces complexity and potential errors the agent needs to navigate.
Okay, let's talk about those 5 environments. They seem specifically chosen. Notion, GitHub, file system, PostgreSQL, Playwright.
Yeah, they cover different types of interaction challenges. You've got the remote services first. Notion tests interaction with remote APIs for documents and databases. GitHub is a big one, project management, Git stuff, CI/CD pipelines, handling issues. They exposed something like 94 different tools just for GitHub.
94 tools? That's a huge action space for the agent to navigate.
It really is. It forces complex planning.
Then you have the other environments, maybe more locally controlled.
Kind of. File system deals with local file operations, creating folders, moving things around. They set up 30 tasks with specific folder structures. PostgreSQL is all about relational databases. The agent needs to generate and run SQL commands using, I think, 9 specific tools.
And finally, Playwright. That's browser automation, right?
Yep. Navigating websites, filling out forms, scraping data from dynamic pages. That uses about 21 different tools, very important for interacting with the modern web.
So that mix, remote APIs, local files, SQL, browser interaction, really covers the basis for agentic tasks.
Definitely. It's designed to be a comprehensive stress test. And remember that average task length, 16.2 execution turns, using about 17.4 tool calls on average. That's not trivial.
Can you give an example? Like, what does a 16-turn task actually look like?
Sure. Take the employee project tracking task in PostgreSQL. The agent doesn't just run one query, it has to create multiple tables first. Then define the relationships, the foreign keys between them, then set up performance indexes, then insert the initial data correctly. That's a lot of steps that have to be right.
Okay, yeah, that's definitely complex. What about GitHub?
Or think about the linting CI workflow on GitHub. The agent needs to first create a new feature branch, then write the config files for the linter, then set up the GitHub Actions workflow YAML file correctly, then create a pull request. And here's the tricky part. It often has to see the linting error reported by the CI check, correct the code based on that feedback, push the fix, and then merge the PR.
Wow, okay. That involves reacting to feedback, state changes, much more than just calling tools.
Exactly. It requires planning, error handling, and managing state across many turns.
All right, we've established this benchmark is seriously tough. Let's get back to those performance numbers. We know GPT-5 Medium hit about 52% pass at 1. How did others stack up?
Well, that 52.56% for GPT-5 Medium was the peak performance, which again means it failed almost half the time on the first try.
Still kind of sobering for a frontier model. What about open source options?
There's a pretty significant gap there. The best open source model they tested was Qwen 3 Coder Plus. It came in at 24.80% pass at 1.
Less than half the performance of the top proprietary one.
Yeah. And most other proprietary models they listed were hovering somewhere between 15% and 30% pass at 1.
So across the board, even the best models are struggling significantly with these complex, realistic workflows.
It's clear that this level of multi-turn agency is far from a solved problem, even for the big players.
You mentioned the interaction load earlier. Some models took a lot more turns than others, like Kimi K2 Instruct averaging almost 27 turns. Did taking more turns help? Does trying harder work?
That's a great question, and the answer seems to be no, not really. That's actually a key insight on efficiency. Models like Kimi that averaged, 27 turns, it often indicated they were getting stuck, maybe in loops, trying the same things over and over. It suggests poor planning, not successful persistence.
So it wasn't brute force winning, it was smarter decision making.
Exactly. The models that did better tended to be more efficient. They used fewer, more targeted tool calls. It wasn't about just throwing more attempts at the wall. And interestingly, this also connects to cost. The paper notes that some of the runs that used the most resources, the most turns, the most expensive runs, actually had lower success rates. Cost doesn't equal performance here.
Okay, that's efficiency. What about where they succeeded or failed? You mentioned an environment gap. What's that about?
Right. The performance wasn't uniform across those 5 environments. There was a clear difference between local and remote services.
Which ones were easier?
The local ones, PostgreSQL and file system, were definitely easier for the models. For instance, GPT-5 Medium, the top performer overall, actually scored over 76% pass at 1 on PostgreSQL tasks.
Much better than its overall 52%. Why would that be?
Well, the thinking is it's likely due to better simulation capabilities and maybe more available training data for those kinds of tasks. File I/O and standard SQL are perhaps more predictable, easier to generate good training examples for.
Okay, so the models are better trained or equipped for those structured local interactions.
Seems like it, but the moment you throw them at the remote services...
Notion and GitHub.
Yeah. That's where the scores really tended to collapse. Most models dropped below 25% pass at 1 on those.
Why are those so much harder? Is it just the API complexity?
It's likely a mix of things. Handling complex, sometimes slow or unpredictable API responses, dealing with potentially messy real-world state in someone else's system, managing authentication, and navigating that huge tool space, especially for GitHub. It points towards a challenge in generalization and probably a lack of sufficient high-quality training data capturing these intricate multi-step interactions with real-world remote platforms.
Okay, this brings us back to what you called the core issue, stability. Let's just quickly redefine those metrics for everyone listening. Pass at 1, pass at 4, and pass 4.
Right. Pass at 1 is simple. Did it work on the first try? Pass at 4 is about coverage. Run it 4 times. Did it succeed at least once? This shows a model can potentially solve it.
But pass 4, That's the tough one.
That's the killer metric for reliability. Pass 4 means all 4 independent runs must succeed. They have to produce the correct final state every single time. That's the standard you'd need for, actually deploying an agent to do real work.
Because you can't have an agent that messes up finances or code 2 out of 3 times.
Exactly. You need consistency. And this is where the results are, frankly, alarming.
Let's look at GPT-5 Medium again. Its pass at 1 was 52%.
Yeah.
What was its pass at 4?
Its pack at 4 actually climbed to 68.5%. So if you ran it 4 times, you had a nearly 70% chance of getting a correct result at least once. It shows the capability is kind of there, sometimes.
But the pass 4, the consistency score.
That plummeted down to 33.86%.
Wow. From 68% chance of success at least once, down to only a 33% chance of success every time across 4 tries.
Yeah. It vividly shows this deep instability. The models might stumble onto the right path occasionally, but they can't reliably reproduce that success over multiple attempts, even on the exact same task. The planning, the context handling over those 16 turns, it's brittle.
And this wasn't just GPT-5 Medium, right? This pattern held.
Oh, yeah, it was systemic. Take Claude Sonnet 4. Its pass at 4 was around 44.88%, but its pass 4 dropped to just 12.60%.
12% reliability.
It's a huge drop across the board. This inconsistency, this lack of robustness is arguably the single biggest blocker for trustworthy agent deployment right now.
Did the paper look into why? Like, could you just make the model think harder? They mentioned reasoning effort.
They did investigate that. They varied the amount of thinking tokens allowed before the model generated its action plan. For the bigger models, like the GPT-5 series, giving them more thinking time did help, especially on those difficult remote tasks like GitHub. For GB5, the performance on GitHub nearly doubled, going from about 27% with low effort to around 50% with high effort.
So more reasoning helps the bigger models plan better for complex tasks.
It seems to. But it wasn't a magic fix.
Especially for smaller models.
Exactly. The smaller models, like GPT-5 Nano, saw very little improvement, maybe 4% to 6% gain. It suggests that if the base model just doesn't have the capacity, simply letting it think longer doesn't fundamentally change its ability to construct and execute a complex 16-step plan correctly. There's a core capability limit.
Okay, so reasoning helps, but isn't enough. Let's get into the actual failure modes. They broke failures down into explicit and implicit. What's the difference?
Explicit failures are obvious. The agent crashes, hits an error, exceeds the turn limit, things like that. You know it failed.
And implicit failures.
Those are much sneakier. The agent runs through all its steps, finishes, and says, I'm done. But the final state of the environment is actually wrong. The Notion page wasn't updated correctly. The data constraints are wrong. The code doesn't actually work.
Ah, so it fails silently. It thinks it succeeded.
Precisely. And these implicit failures were dominant. For most models, they accounted for over 50% of the errors. For some top models, like GPT-5 High, it was over 80%.
Over 80% of failures were the model getting it subtly wrong without realizing. That's concerning.
It really is. It points to fundamental gaps in reasoning, planning, or understanding the tool's effects, rather than just, say, hitting an API error.
What about the explicit failures? Were there patterns there?
They were more model-specific. For example, GPT-5 High tended to run into context window overflow more often. Handling the long history across 16-plus turns became an issue.
Okay, so memory management is a factor in long tasks.
Seems like it. And Kimi K2 Instruct, the one that took many turns, it frequently failed by hitting the turn limit exceeded error. Which
confirms our earlier point. It was getting stuck in loops, not making progress.
Exactly. It highlights that overcalling mode we talked about.
So the big takeaway from MCPMark seems to be that successful agency isn't just about having the capability to use tools. It's about strategic, efficient, and reliable use of those tools.
You nailed it. MCPMark really forces the community to look beyond, can the model call this API, to can the model construct and reliably execute a 16-step plan using multiple tools correctly, managing state and errors along the way.
It shifts the focus from mere competence to robust strategic execution.
Yes.
Okay, wrapping this up, what's the bottom line here? What does MCPMark tell us about the road ahead for agent development?
Well, it clearly establishes a much-needed realistic benchmark for stress testing agents in complex, multi-component scenarios. It moves us beyond toy problems, and it starkly highlights the key challenges. Agent stability is low, generalization to complex remote services is weak, and sophisticated planning and error recovery are critical missing pieces. We need to move beyond simple, reactive tool use.
And that massive drop in the pass 4 scores. That reliability crisis is the big practical roadblock for anyone wanting to actually deploy these things.
Absolutely. The bottleneck isn't just the LLM's raw intelligence. It's the agent's ability to manage this growing history of actions, observations, and its own internal state over long interactions, and crucially, to do it reliably every time, even when things go slightly wrong.
Right. Which leaves us, and you listening, with a final thought to chew on. Given that even our best models are only achieving around 33% reliability, past 4, on these complex, realistic tasks, what's the path forward? Is it just bigger models? Or do we need fundamentally new approaches within the agent framework itself? Maybe novel ways to summarize context, compress history, or implement more explicit self-correction and robust error-handling loops without just making the models impossibly slow or expensive.
That seems to be the core question. How do we build agents that aren't just capable sometimes, but are dependably correct? The future of truly useful AI agents probably hinges on solving that reliability problem.